Assalamualaikum and a very good day to all of the panels. Professor Madya in Senior Technologist Dr. Muhammad Syukur bin Saleh, in Senior Dr. Muhammad Rizwan bin Jamli, and Professor Madya Dr. Liu Pei Jun. My name is Nur Athirah binti Muhammad Zailani and my MATRIC number is B0518200101. I will present my final year project. The title is Machining Parameters Optimization during machining of alumina using CO2 laser. For your information, the supervisor for this project is Professor Madya Dr. Matnizam bin Abdul Rahman. This presentation is divided into 5 parts. First, introduction. Next, the literature review. Third, the methodology. Then the result and discussion. And lastly, the conclusion. Alumina, usually referred as aluminium oxide Al2O3, has a brilliant white color and extraordinary hardness. It is one of the most widely used structural ceramic material with various applications in the industry, including spark plug insulator and tap washer. The material's brittleness is the main concern during the machining process, as it is hard to be machined. The strong ionic covalent bonds in alumina make it hard, brittle, and do not yield under load. According to Bilal, there are various kinds of machining of alumina, such as milling, drilling, and turning. However, using these conventional machining techniques, the material experiences high cutting forces and extensive tool wear. This project will focus on one of the potential processes, that are CO2 laser machining, because the technology of CO2 laser is often used for processing of cutting and welding thick material, because it has good control of the beam power and the absence of mechanical contact with the workpiece. Main issue in the machining of alumina using conventional method is that it will result with defect and excessive tool wear because of the high hardness and brittleness. Moreover, the material removal is in the form of bigger chunks, and sharp-edged regions facilitate the brittle failure of the work. The surface damage during machining the ceramics caused by these techniques could reduce the strength and efficiency of the material. Consequently, the crucial phase in manufacturing the ceramic material has to machine the material with excellent quality. There are two objectives for this project. There are to optimize the CO2 laser machining process parameters in order to maximize the quality of drill hole using design of experiment method, and to identify the significant parameter that influence the quality of drill hole using ANOVA analysis. Next, for Chapter 2, I will proceed with the literature review. I have summarized the journals that are related into this table. The first journal by Baratish examined the effects of laser parameters using CO2 laser percussion drilling on 2 mm thick alumina plates. The machining parameters used are frequency, laser power, and scanning speed. The results stated that entrance circularity is influenced by laser power and hole diameter. HZ thickness decreased with increase in pulse frequency and constant laser power. Secondly, Baratish 2017 study on the effects of laser parameters on the drilling responses of alumina-coated aluminium. The machining parameters used are frequency, laser power, and piercing time. From the journal, the results stated that exit hole circularity increased with increase in the frequency and piercing time. Other than that, frequency influenced entrance circularity. Piercing time significantly influenced taper angle, HZ, and exit circularity. The third journal by Rand investigate the morphology, diameter, taper angle, cross-section area, and sidewall characteristic of the holes. Water-assisted femtosecond laser drilling method used to drill holes in alumina ceramics. The machining parameters used are scanning speed, pulse repetition rate, and single pulse energy. The results stated that the whole cross-section area increased with an increase in the pulse repetition rate in air and decreased with an increase in the pulse repetition rate in water. Chapter 3, I will proceed with the methodology. This is the flowchart for this project. Firstly is by design the experiment. The material used is 99.7% alumina ceramic plate with 3 mm thickness, and the experimental design for this project is generated using Minitab software version 20.2. Full factorial method will be used with 2 levels, 2 factors, and 3 center points. The machining parameters evaluated are laser power from 50 watt to 150 watt and frequency from 1000 Hz to 3000 Hz. The output responses for this project are heat affected zone and taper angle. Next, the execution of the experiment. The experiment was executed by using the experimental design, and the data will be collected during the experiment using scanning electron microscope (SEM) machine. The data analysis is done by using Design Expert software version 6.0.8. Main factor analysis, interaction analysis, and 3D response surface will be done by using analysis of variance ANOVA method. This table shows the design of experiment that generated using BINTI software version 20.2. From the table, several runs of experiment need to be done. The evaluated parameters for this project are laser power and frequency, and the fixed parameters are gas pressure, cutting speed, and duty cycle. I will explain on how to calculate the heat affected zone. SEM machine will be used to produce image of the sample that had been drilled. Then the data of HAZ diameter and entry hole diameter need to be measured and inserted in the equation. Next is taper angle. Taper means to become smaller or narrower towards one end. It refers to a piece of material or a hole where its diameter decreases compared to diameter on other end. For measuring the taper of laser drill hole, the entry diameter and the exit diameter as shown in figure were measured using SEM machine and inserted in the equation. As for chapter 4, I will proceed with the results and discussion. The table shows the result obtained for this project. The picture shows the maximum and minimum value. For heat affected zone, the highest value is run number 2 and smallest value is run number 5. For taper angle, the highest value is run number 2 and the smallest value is run number 4. Result obtained from Design Expert software. From here we can see that the model F value of 13.18 implies the model is significant. In terms of significance of the parameters that give influence are both model A and B. However, the interaction between the two parameters are not significant. I will discuss the result obtained for the heat affected zone. Here we can see the main factor analysis for laser power and frequency. From the graph, as laser power and frequency increases, the HAZ will decrease significantly. We can see two lines that are parallel at the interaction analysis. That means that there are no interaction between A and B, and the 3D response surface plot gives the overall view of the impact of each parameters to the output response. The results were in agreement with British et al. 2017 that said HAZ increased with decrease in laser power because of the fast temperature decay caused by higher thermal conductivity. Next, I will discuss the result obtained for taper angle. Here we can see the main factor analysis for laser power and frequency. From the graph, as laser power increases, the taper angle will decrease. However, when frequency increases, the taper angle will increase. The interaction graph shows that there is interaction between factor A and B, and from 3D response surface plot we can know that to get lower taper angle, we need to use lower frequency and higher laser power. The results were in agreement with British et al. 2013 that said that the laser power increases the diameter at the entrance and at the exit increase, which result in reduced taper. Next, we go for the validation process. Table 8 shows the range of parameters that have been taken from ANOVA analysis to run the validation test, and we can see the result for the validation at table 9. Table 10 shows the SEM image for entry and exit hole for each experiment. Next, we can calculate the percentage error for each validation test by using the mathematical model that we get from ANOVA analysis. The percentage error for run number 1 is 9.6% and 6.29% for run number 2, and for run number 3 is 15.84%. The average percentage error is 10.57%. For taper angle, the percentage error for run number 1 is 7.18% and 50.58% for run number 2, and for run number 3 is 8.68%. The average percentage error for taper angle is 10.48%. Lastly, we can conclude that the ANOVA analysis indicated that the higher laser power and higher frequency are preferred to achieve optimal machining parameters. The significant parameter that influenced HAZ and taper angle based on ANOVA analysis was laser power. Next, the HAZ increased with decrease in laser power at constant duty cycle. Last but not least, taper angle increased in decreasing in laser power. For the recommendation for future works to be implemented are: compare the result from different thickness of alumina ceramics. Next, use other machining parameters such as duty cycle or pressing time. That's all from me. Thank you for lending me your ears.